Okay, let's start. So far we have discussed about 1D flow, and in that 1D flow we have also seen the nonlinear differential equation, right? And from now on we will be discussing about 2D flows. Okay, so before we get into the nonlinear system, we will first focus on the linear system. Okay, so how that linear system will look like. So in a 2D flow, say we have two variables, one is x, another one is y. Okay, and in order to be linear, this x and y are related to x dot in this following manner. Okay, where this parameter a, b, c and d are the system parameters which are just constant. Okay, which are just constant. So this is how a general 2D linear system will look. Okay, now the same system we could represent it as a or in the matrix form. Okay, like x dot is equal to ax, where x dot is a vector. Okay, or x is a vector which is x which contains x and y. Okay, by x dot we mean x dot and y dot. Okay, so the same equation which is written here can be written in this manner. Okay, so that's another way of representing the 2D linear system. Now let's take this example, okay, which is mx double dot plus kx is equal to 0, which is a very known equation, which is a simple harmonic oscillator, right? If there is a spring mass system, then this equation will emerge. Okay, where in the spring mass system, m represents the mass of this body, and then x represents the displacement with respect to the equilibrium position, k represents the stiffness of this spring, and x double dot represents what is the acceleration of this mass. Okay, now this is an equation governing differential equation. Now we are going to see how to write this equation into this form or this form. Okay, so we have already seen this one, but anyway, we'll see it once again. Okay, so what I'm going to do is I'm going to assume, so this is going to have two independent variables, where one of the independent variable is x, the displacement, and the other independent variable is x dot. Okay, so the other independent variable is x dot, which means velocity. Okay, so now I have two state variables. One is current position x, another one is velocity. Here instead of x dot they have put v, okay, to assign a new variable. Now I need to know how x is evolving, which means what is x dot, and also we need to know what is v dot. Okay, that we have to obtain from this equation. Let's see. So we know what is x dot, which is equal to v, right? So that's the definition. Now what is v dot? That we will get it from this equation. So in the place of x double dot, we could put v dot, and if we put v dot, we will get this equation. Okay, so now this is the equation. Actually this equation I have represented it in this form, which results in this equation. Okay. Now, let's say we know from our a little bit of vibration analysis that K by M represents the frequency of the system, the square of the frequency of the system, which means omega square is equal to K by M. So let me replace that. If I replace that, what will I get is x dot is equal to V, and V dot is equal to minus omega square x. Okay. So now that's the system. And okay, now I have this one. Should I solve it in order to understand how the system is behaving? Well, it's a linear system and it is easy to solve. However, what we are going to do is we are going to just plot x versus v, and in this x versus v we are going to plot this equation somehow, and then we will identify how the system behaves. Okay, so this is the plane, which is also known as phase plane or phase space. Okay, so when I have a space which is of all the state variables, then it's called phase space. Okay, and in this phase space, each point represents a particular state of the system. Okay, now for example, say my system is at this point. Okay, what does that mean? It means it has some x value, okay, but 0 v value. What does that mean? It means the x value is something of positive value and v is 0, which means velocity is 0 but it's been stretched. Okay, so that's what this particular point represents. Okay, let's see what is this particular point represents. Here it means it has some v value, the positive v, but 0x. What does that mean? It means, again in this picture, the displacement is 0, which means it's exactly at the neutral position, but it's moving. Okay, the velocity is not 0, the mass is moving at that particular instant of time. Okay, so that's what this particular point represents. Okay, now what is our interest is, say I am at some particular point, okay, and then how my system is going to evolve, or how my state is going to change. Okay, and that particular if I collect all the points which the state experience, and those collection of points or the locus of point is known as a trajectory. Okay, so we will be interested to know what is its trajectory. Okay, for a given system, what is the trajectory? Okay, let's see roughly how to identify the trajectory for this system. Say I'm at this point. Okay, so this is some positive v value and 0x value. Now look at this equation. So some positive v value, which means x dot is some positive value, but x value is 0, so v dot is 0. So there it means because of v, there's going to be a change in x, and that change is positive. Okay, which means x is going to increase. What about v? V is not going to change because x is 0 at that particular state, right? And therefore we will have, so what the system will do is the system will try to go along this direction. Okay, so like that for each and every point I have to draw a vector. Okay, so which is the draw a vector in this particular phase space, and if we do that for this system, what we will get is this particular picture. Okay, so from this particular picture we could somehow understand how the system is going to behave. Okay, so maybe it seems like when the system is at this position, it's going here, and then it's going here, 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 and it's circling. Okay, it seems like that. And if it starts from here, it's going to circle in this manner. Okay, so this is what we understood, but what does that mean, circling? Okay, so let's try to understand that part. Okay, so initially the velocity is some positive value, but displacement is 0. Okay, so we have an initial excitation, but the displacement is 0. What's happening? It's keep on stretching. Okay, so velocity is in this direction, but the displacement is 0, so it's keep on stretching. Okay, so that's what we observe here. So maybe the system will go like this until it reaches some value, okay, where all the kinetic energy convert into a spring energy, and after that what will happen? The spring is being stretched, so it will try to come back to its equilibrium position. So that's what's happening. But while it's coming back to its equilibrium position, it will gain the velocity, but in the opposite direction, right? So that's what this part says. And once it reaches equilibrium position, then there will be a velocity. So because of the inertia, the system will not let it stop, so it will go further, and then at this particular point it will be compressed to an extreme state, so it will start pulling back towards the equilibrium position. So it will come here once again, and it will do this behavior continuously. Okay, so this is how we will try to understand the problem. And if we try to make a trajectory, okay, and the trajectory will look like this. Okay, so once I start at this point, I will go all the way and then come back to this point. If I start from here, which means instead of giving a high velocity, if I give a low velocity, then I will have a different trajectory path, a different trajectory. Okay, so this kind of picture, okay, where we will have a lot of trajectories, okay, is known as phase portrait. Okay, so by looking at the phase portrait, we will be able to understand if some particular state is my initial condition, then how the system is going to behave. So just by looking at this picture, we can have an understanding. Okay, just by looking at the phase portrait, we can have an understanding of how the system is going to behave. Okay, so in the following lectures, what we will do is we will see how to construct such face portrait and how to read the face portrait, okay, and how the face portrait is going to look like for different cases. So those are the things we will learn. First we will do that just for linear system, and then we will introduce the nonlinearity. Okay, thank you.